Okay guys, in this video we're going to talk eventually about what's called the impulse momentum theorem. If you're saying to yourself, I don't know what impulse is, that's fine, we're going to get to it. The impulse momentum theorem, very useful tool in physics. So maybe to just get into it, let's remember a couple things that we had said about momentum when we discussed momentum conservation. Momentum conservation, we noted, is a really useful tool because momentum is conserved in some cases where energy is not. So in particular, we talked about cases where there's an internal, or where there are internal forces acting on an object, such as a collision. If two cars smash into each other, obviously they exert forces on each other. And since they're exerting forces on each other, we call that an internal force. It's internal, it's inside the system meaning the two cars. But of course, there are ways in which an object's momentum could change, and that's what I'd like to think about. That's what's going to get us into impulse. So for instance, let's just imagine that I've got some kind of surface, and we'll imagine for now that this is just some kind of frictionless surface. And then on this surface, I've got some kind of a block here. Here's a block on that frictionless surface. Here it is. And we could say, for instance, we might start by noting, let's say that this block's velocity is 0 to start. So we'll say V initial is 0. So it has no momentum. So I can say P initial is also 0. Remember, P is our abbreviation for momentum. So how could I change the momentum of this block? How could I give it momentum? Well, I would give it momentum by giving it velocity, and we would do that by applying a force. So I could come in here and apply a force on that block, and if I apply a force, that's going to cause the velocity to change and the momentum to increase. So maybe we could write that out. The applied force is going to cause an increase in the velocity, which means that there's going to be an increase in the momentum. All right, so the question might be something like, by how much does the momentum increase as a result of this force, this outside force? So we're assuming the applied force here is an outside force. Maybe we could just sort of make a quick note of that. This guy here is an outside force. Outside force, not an inside force. In other words, some object that's not part of the block is coming and pushing on the thing. All right, so here we go. So that's our question. By how much does the momentum increase as a result of the applied force? Well, I hope it's obvious to you that you need some more information to answer the question. In particular, it might be clear to you that I need to know how long has that force been applied. So the answer to this question is going to depend. It depends on how long the force is applied. In other words, I need to know the delta t. I need to know the time that force is applied. And if I know the time, you might figure, just based on what we've learned about Newton's laws in kinematics, that if you had time, you could figure out what the change in velocity is going to be. Assuming the mass of the block doesn't change, which it shouldn't, then we would know the change in momentum. And if that was your instinct, you're absolutely right. And this is going to get us into the impulse momentum theorem. So I'm going to do a little bit of a derivation here that you don't technically need to know, but I thought it would be worth kind of showing you where the impulse momentum theorem comes from. So maybe I'll just do this as a little aside. So we could start with F equals ma. We know that by Newton's second law, the force equals the mass times the acceleration. But I also know this other equation, that V final equals V initial plus AT. And if I take this equation and solve this equation for A, I could write A equals V final minus V initial times T. I just solved this equation for A. And now I could take this thing here, this expression here, and plug it in right there for A, since that's another name for A, and I would get something that looks like this. I would get F equals M times V final minus V initial all over T. Now I might simplify this. The first thing I might do here is I might go ahead and distribute the M, and then I would get F equals mv final minus mv initial over t. This is, sorry guys, this is right here, that's supposed to say v initial, not vt. Right there, it's supposed to say v initial. V initial. All right, back to this now. The last thing I'm going to do is take the t and move it on over to the left-hand side by multiplying both sides by t, and I get f times t equals mv final minus mv initial. And believe it or not, this is the impulse momentum theorem. That's what this thing is. This is the impulse momentum theorem right here. Impulse, and we'll break it down in a minute, but this is the impulse momentum theorem. So I just do that derivation just to show you that it doesn't come out of nowhere. So what we have here, to break it down into a little bit more depth, on the left-hand side of the equation, this is impulse. So to define it, impulse is a force exerted over a time, over a period of time. It has a symbol. I don't really care about the symbol too much, but the symbol for impulse, it's abbreviated with the letter J. And so I could say J equals F times T. That is the left-hand side. That is the impulse right here. Okay. The unit here is newtons times meter, or times seconds rather, not meters, seconds. Newtons times seconds. F is in newtons, T is in seconds, so it's Newton times seconds. And what this equation tells me, if I go over the right-hand side now, is that impulse, F times T, equals mv final minus mv initial. Well, that's change in momentum. This is P final minus P initial. That is the change in momentum. So what this is saying is the impulse, the force multiplied by the time, equals the change in momentum of the object. That's the impulse momentum theorem. So maybe coming back up to this thing here, if I knew that this force was applied over a time, let's say this force is applied for some time, we'll call it delta t, just to use the variable, then what could I say? Well, I could solve this question here by how much does the momentum increase. Now with delta t, I could make a statement. I could say that F times delta t, F times delta t, Fa times delta t, is going to be equal to mv final minus mv initial. And I told you that v initial was 0, right? We noted that v initial is 0, so this term is 0. So I could just say that the momentum changes by Fa times delta t, because that's going to be equal to mv final in this case. Okay. So that's the impulse momentum theorem. Maybe I'll state it up again, maybe slightly in a slightly cleaner fashion up here for you. The impulse is F times T, and that impulse equals the change in momentum, which is mv final minus mv initial. So this will be our nice clean version here of the impulse momentum theorem. Put a nice fat box around it. There it is, the impulse momentum theorem. Now, the impulse momentum theorem is helpful for problem solving, but it also kind of lets you explain maybe some common everyday experiences that you might have. So, for instance, I'll try to provide a few examples. Let's imagine that you are say doing some rock climbing. You're in the gym and you're on the rock wall. Right, so you got these little handholds and footholds, and there you are. You're trying to climb up this thing. You're trying to climb up the rock wall, in this direction up. But of course, you're above the ground, and there's always a chance that you are going to, one of your handholds is going to fail, and that you're going to come falling down, down, and hit the ground. So what you do is on the ground beneath you, you put a nice, fat little soft mat, or you ought to anyway. It's a good idea to. So you would come down here maybe, and you'd have some fat mat right here. Maybe I'll make that a little bit bigger, something like this. This big fat mat right here. So that if you did fall, you would fall on this soft squishy mat. And the soft squishy mat would make it so that your fall didn't hurt too much. And of course, the question might be why. It's fairly obvious that a soft cushy mat is going to break your fall and make you much less likely to hurt yourself, but why? So, we could wonder about that. Why does the mat reduce the risk of injury? I could put it in a very formal way. And you might just say, oh, because it's soft, but okay, that doesn't really help us. Impulse momentum theorem, however, does. If we go down to the impulse momentum theorem, what's the mat going to do? Well, when you come and you fall, so here you are, you've fallen, and now you're about to hit the mat. There you are, you're about to hit the mat. You have momentum. You have some mv initial in this direction. But the mat is going to take that mv initial and bring it to 0. You are going to stop as a result of the collision. The mat will stop you. It will bring your mv to 0. So what does the mat do? Well, if we go back to the equation here, what the mat's going to do is it's going to increase the amount of time for that change in momentum. And by increasing the amount of time, it's going to decrease the amount of force. In other words, I might put it this way. Without the mat, we would have a collision with the hard floor here that would happen over a very, very small t. And if the t is small, then the F has to be very, very big. With the mat, the time is much bigger. And if the time is much bigger, then the force doesn't have to be quite so much. So either way, either with the mat here or without the mat here, you're going to have the same impulse. You're going to go from some mv initial down to 0. Either with the mat or without the mat, that's going to happen. What the mat does, the mat causes this time to increase, thereby decreasing the force so that it doesn't hurt so much. Okay? So that the mat increases the time of the impact to decrease the force of impact. So we could even write that out. Let's use a pen. The mat increases the time of impact to decrease the force. I hope that sort of kind of intuitively makes sense. There are lots of different examples of this sort that we might think of. So for instance, airbags, right? You're driving along in the car and you get into a car crash. Your head could hit the dashboard. If your head were to hit the dashboard, the time would be really, really small, so the force again would have to be big. That's like hitting the ground without the mat. With the airbag's slightly squishy, so it's going to increase the T, so I get a bigger T, and thereby I don't have to have quite so much F, not quite so much force, and so I'm less likely to get injured. That's again the impulse momentum theorem.